Okay, so we're going to talk about functions, and we'll talk about functions today and tomorrow. But in order to talk about functions, we have to start someplace a little differently. We want to start with something called a relation. Okay, so a relation, this is defined in different ways, but sometimes it sounds complicated. It's not. A relation is literally just any relationship between values of x and values of y, so inputs and outputs. That's it. It could be an equation, and usually for us it's going to end up being an equation, but it doesn't have to be. We're just going to start off with some examples that aren't equations. It just has to be anything that relates the first component of an ordered pair, which for us is almost always x, right? And the second component of an ordered pair, which we call y. If we take all of the input values, or the x values together, we call that the domain, right? Those are the values we can input into the function, or the relation. And then the outputs, the values that are spit out by the relation, or the equation, or whatever it is, we call that the range. So let's look at an example. So this is a relation, okay? So it's just a bunch of ordered pairs, right? If we look at this, look at these funny script brackets at the end. What do those things mean? You know?
All of it's together.
All of it's together, right? That's true. It's all taken together. In fact, that means it's a set, right? Anything that's inside the script brackets, we're defining that as a set of something. We call that set notation. So a lot of times when we talk about sets, we'll talk about if it's something like this where we have discrete parts that are just gathered up in a set, we call each one of the things that the set contains an element. Okay? This might seem like an insignificant question, but it's actually pretty important. How many elements are there in this set?
5.
5 is right. It's not 10. It's 5. You might look at this and say 1, 2, 2. There's 10 numbers up there, but if we group these things together, there's an ordered pair, right? There's an ordered pair, etc. And so there's a total of 5 ordered pairs, okay, in our set. Each one of those has an x coordinate and a y coordinate, right? Which one's the input? X or y?
X.
The x. X is always going to be the input, and y is going to be the output. Okay? How do you remember that? Well, x alphabetically goes before y, I goes before o, in before out. Okay? So they're the same order. So then if we take the set of all the input values, meaning the x values, we call that the domain. Can anybody tell me then, how would I define the domain? It's a set, right? It's a set of all the values that we can input into our relation. What do you think? What's that going to look like? I'm going to have to open up a set of script brackets for a set, but what goes inside those brackets? What values?
The x's.
Yeah, so what are those?
1, 2, 3, 4, 5.
Exactly. That's it. Okay. Okay, so what about the range? Right, so the range is the set of all the output values, so the y values. What's that going to look like?
2, 4, 6, 8, 10.
Yeah, it's just going to be the set of the values 2, 4, 6, 8, 10.
So the domain's always going to be the x?
Yes. Domain's the x value. Set of all the x values, range is the set of the y values. Now, it might turn out later that we don't use x's and y's. Like in physics right now, for example, we're talking about, let's say we're talking about velocity, right? And so the input values there are going to be times, and the output values are going to be the velocities for an object at each time.
It'll always be the same thing?
It's always going to be the same kind of thing. Whatever is the first coordinate. So for us, almost always it's going to be x and y. So the input, the first part of the ordered pair is always the input, x for us. Second part is always the output, which for us is y. Okay? All right, so there's one example. Let's try another one. Okay, what about that? That looks a little weird. How many elements are in that set?
5.
5. Okay. Good. So let's look at the first element. The first element is a weird-looking ordered pair. What do you suppose that means?
Odd
Odd what?
number.
Odd number. Okay, so this first ordered pair is saying if I input an odd number, what's the output going to be? 1. This one tells me if I input an even number, the output is, input an odd number, the output is, etc., right? Okay, so what's the domain of this one?
Odd, even, odd, even, odd, even.
Okay, so odd, even, odd, even, odd, even, or odd, even, odd, even, odd. But that's the same as that, isn't it?
So odd, even?
Just odd, even, right? I don't need to repeat, okay? Those are the two different values two different things that I could input into my relation, right? What are the outputs?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5.
That
Make sense? Okay, no big deal, right? We're just making in math we call it a mapping. We're just mapping inputs to outputs, okay? Okay, how about something like this? That's a different way of representing it, but it's the same idea. Now, instead of writing the set as a bunch of ordered pairs, we're writing the set using what's called a Venn diagram, right? So just this blob over here, everything inside of the border is meant to be, that's inside a single set, which we're going to call the inputs. And then the outputs are the set over here. So what's the domain of that relation? PQR. Right? And if they're letters, we'd write them in alphabetical order. If they're numbers, we just would write them in numerical order. Okay? What's the range? MN. No big deal. Okay. How about something like that? Same idea, different form. Now we're writing it as a table. Okay, these are the input values and the corresponding output values. So domain?
7, 6, 8. -7.
-7, 6, 8.
And then
We agree? Range?
3.
3. That's it. Okay. So now, let's go one step further. Okay, let's talk about a specific kind of relation. This is really important because this is what we really wanted to get to. Most of the time we're interested in dealing with relations that are functions. Functions are a subset of relations. In other words, there are relations that are not functions, but all functions are a type of relation. Does that make sense? So a function is a special relation that assigns a single element in the range to each element in the domain. In other words, here's another way of saying that. For each input, there is exactly one output. That's the definition of a function. For every input, so typically for us, for each value of x, there's only going to be one output, any value of y, right? What that means is, and this will make more sense in just a second, that no input values or x values are repeated if we're writing it as ordered pairs, for example. Okay, so let's look at the examples we just considered. Let's go back and ask the question, all right, we found domain and range, but now are they functions? Do they meet that criteria? Okay, so how about this guy? Okay, what do you think? We know on this one, you already told me what the domain and the range were, but now the question is the relation a function?
How do we know that?
Because it has to meet the criteria that for every x value, there's exactly one y value. For every input, there's only one output.
Yeah.
It works, doesn't it? Right? For no matter what x, if I put in an x value of 4, the output is 8. There's only one output, right? Okay. So it works. No x values are repeated. Every number in the domain is assigned to only one value in the range. Okay? Okay, let's look at another one. Maybe. Oops, I guess the next page. how about this guy? So, how about that example? So there's our domain, and there's our range. Is the relation a function? Shaking your head, you're right. How come?
Because they repeat themselves in the X like.
Okay, good. So if I input, for example, an odd number, right? If I input an odd number, well, that maps to the output value 1, but it also maps to 3, and it also maps to 5. Doesn't work.
So X can't repeat itself?
X can't repeat itself. Yeah, for a single input value, for a single X value, I can't have more than one output or Y value. In this case, I do, right? So that's not. Okay, and same thing works for evens, right? And input of an even number outputs two different outputs, and so it fails for that reason also, right? Okay, how about one like that we looked at? There was our domain and our range.
Yes.
Yeah, good. Usually people, a lot of times, first time through, will say no on this one. And the reason they'll say no is because both Q and R map to N. But it's okay, isn't it?
Multiple Y's, or like repeating Y's.
There could be repeating Y's, but there just can't be repeating X's, right? Each one of these, if I put in Q, I get one answer out. I get N. If I put in P, I get out M. If I put in R, I get one answer out. It's N. Does it matter that I got the same output as I got with Q? No, it doesn't matter. I still only got one output for each input, right? So that is a function. Okay? How about this guy?
Yes.
Everybody agree that's pretty obviously a function. Okay, that one works. Yeah. Let's look at one more here. How about this one?
No.
No, got a problem, don't we?
Repeating
Everybody see that one?
X.
Yeah, repeating Q.
Yeah, that one doesn't work because now the input Q gives me two outputs. So if we're looking at this in terms of, we said if we're looking at it in terms of ordered pairs or a table, repeating X values would have been the giveaway that it wasn't a function. What if we're using Venn diagrams like this? What's different about this one compared to that one? What about the arrows here immediately says, problem?
There's two coming from the X.
Yeah, there's two arrows coming from one input. You know right away, that's no function. Now, later on in the class, we'll come back and revisit this when we're talking about inverses of functions and things. And we'll say, we call this a one-to-one function because each input has one arrow leaving it, right? It only maps to one output. We'll call this a many-to-one function because there's a situation here where two different inputs happen to have the same output. So many to one. And this we'll call a one-to-many relation. It's not a function, right? Because one input maps to many outputs.
And the one above would just be a one-to-one?
One-to-one. Okay? But just so I just brought that up. We're not going to deal with that now, but later on you'll go, oh, I remember that. I remember talking about that. Okay. How about this guy? We looked at this. There was the domain and range. Is that a function?
Yes.
Yeah, no problem, right? No X values repeat, right? Okay. Guess that's all there is on that page. Good, good. You guys are getting this. This is good. How about that one?
Same one.
Oh, same one. Whoops.
So yes.
Yes, it is. Okay, let's graph it. Did I miss one here?
No, I think that was the last one we did.
I think it was. Yeah, we're good. Okay. So, yeah, let's graph this one. So that one is a function, right? So what does it mean? What I want to look at here is, yeah, it's a function, but it's a little weird because, not weird, but it's unique in that the outputs are all the same. I want to ask now, what's that going to mean in terms of the graphs of these points? If I look, these are really just ordered pairs, aren't they? An X value and a Y value. If I graph those points on the plane, what is caused by the fact that all the outputs are the same?
Drawers.
Say it again?
Yeah.
They're in a line. Which kind of line?
Like this. on this one.
It's going sideways.
Well, so horizontal, they line up horizontally, don't they? If I go, so this one's over 8 and up 3, this one's over 6 and up 3, this one's -7 and up 3, and notice that they line up horizontally. Okay? I mean, just interesting, right? Not a huge deal, but that's just how that manifests itself, right? Okay, now let's look at this guy. Okay, that is not a function, right? Clearly not a function because we've got repeated x values, right? Now, this is important. Let's look at what happens in a situation like this where we have repeated x values. Okay? If I graph these, what happens with these? So I've got over 7 up 1, over 7 down 4, over 7 down 6. What do you notice about those?
They're just one line.
They line up vertically. Doesn't that make sense? Now think about this, what we talked about here with our definition of a function. If we get a relation that violates that rule, so it's not a function, so a single input maps to different outputs, well, the input is an x value, right? The outputs are y values. Think what that means. If one x value maps to different y values, that implies that they line up vertically, right? So that's the hallmark. That's kind of the red flag that we see when we're looking at a graph. If we're going the other direction, what if I had shown you this graph and asked the question, is that going to be a function? Now you'd notice, say, no, it's not, because these points line up vertically. One x value has multiple y values, right? Okay, so let's look at some continuous graphs. And you tell me, is that a function?
Yes.
It is. It is, right? Because if I grab this vertical line and drag it across, does it ever intersect the function in more than one place? No. We call that the vertical line test. Remember that from Algebra 1? Oh, okay. Well, that's important. So this is a simple test you can always do for a graph. If you want to know if the graph is a function, you just drag a vertical line across it. You know, you can do it in your mind. But if the vertical line never intersects the graph in more than one place, then it must be a function because every x value only has one y value. Otherwise, there would have been vertically aligned parts, right? So that is a function. How about that guy? No, fails the vertical line test, right? That one, problems. All the, like there, for example. Look, there's an intersection and there's an intersection. Right? Doesn't work. Can't be a function. A single x input gives us back more than one y output. Okay? How about that?
Yeah.
Okay, where's there a problem?
On the far left.
Yeah, so that one's fine. That's only one. That's good, 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 good. Everybody see what I mean by good?
Yeah.
Okay, yeah. Oh, problems. Right? Okay, those line up, so it's not a function. Okay, good. So now, next issue then that I want to look at is function notation, right? Function notation. So we've got this idea that functions are very useful to us. We use functions all the time. What a function does, and we'll talk more about this, a function is kind of like a machine where you're going to input some stuff, it's going to process it and output some stuff, right? Just like a machine in a factory on a farm or something, right? So in this case, how do we say this? If we're trying to, for example, calculate the volumes of spheres of radius r, right? Our formula for the volume of a sphere is 4/3 times pi times the radius cubed, right? If we want to write that as a function using function notation, we would write it like this. Because what does this tell us? This is this v, and then right next to it is in parentheses an r. That's function notation. Does that mean v times r? It doesn't. It means something different. We would say that in math, we would say volume as a function of radius, or v as a function of r, or the shortcut would be just v of r. What that means is, whatever is inside the parentheses, that's where we're shoveling the stuff into the machine, right? That's the input. So that's telling us that the input values in this case are going to be radius, okay? The function is going to perform a calculation and output volume, a calculated volume, right? So that we would say this, the way we would say this in math, we were talking about this in my physics class or calculus class, we'd say V of R equals 4/3 pi r cubed, okay? What do you suppose it means if we do something like, what if I do something like that then? What do you think that means if I say a 1 inside the parentheses? What am I doing? I'm using that function notation. I'm using the function V of R that I defined up there. But what am I inputting? What's that say I'm inputting? 1. I'm taking a value of the radius equal to 1. We won't worry about units, right? If I input a value of 1, what is the function machine going to output? Well, I'm just going to use that formula, right? I would plug in 1 for R, so I'd get 4/3 times pi, and where I used to have an R, I'm plugging in a 1 specifically. What's 1 cubed? 1. So I just end up with 4/3 pi is my output. You see that? Right? And so what does this work out to be then? If I were graphing this, here's an example where we're not using x's and y's, right? But if we were to graph this, and this is what I really want you guys to see, because we do this a lot in calculus and physics, for example. We'll graph stuff that, maybe aren't x's and y's. In this case, instead of an x, our input value, right, was r. Normally that would be an x. So that's the r-axis, and that's the v-axis. And if I go over 1, I go up that much. It's telling me that for a value of radius that's 1, the output value, normally the y value, would be 4/3 pi. So this is just an ordered pair, right? We could graph it if we wanted to. We don't have to, but we could graph it. It would mean something, right? If I were to do a graph of radius versus volume, this is what I'd get. I would get something kind of like this that just went, and that's pretty meaningful to us, right? I'm jumping way ahead here, but I want you just to see how useful this could be. This is what we call a math model, where I've got this function. And then how did I get that? Well, because I know what a cubic function looks like. If I have y equals x cubed, it just goes up like that, right? So if v equals r cubed times some number, right? That's just going to, we'll talk more about that later. That's just going to stretch it vertically. Don't get lost on this. Don't panic. I mean, we're looking way ahead here. But this is pretty cool. This tells us as we increase r, the volume is getting bigger more and more rapidly. That tells us something significant. Like, for example, this is, you guys probably don't think about this stuff very often, but I want you to, my biggest goal is that you'll leave the class and kind of think about this stuff maybe at a little different level. Have you ever noticed when you're blowing up a balloon, like for a birthday party or something, when you first start huffing on it and, blowing air into the balloon, it gets big really fast, doesn't it? It just springs up, right? But once it's pretty big, what do you notice? Yeah, you blow and blow and blow, and it just doesn't seem to grow very much, right? Well, that's all because of that curve right there, honestly. That's all that has to do with, right? It takes a lot of extra volume to make the radius go up a little bit once you get further up this curve, right? And when you're blowing air into the balloon, aren't you just putting volume of air into the balloon? And you're watching the radius get bigger, right? See what I'm saying? So the math really tells you why that is the way it is. Okay? Questions on that? Okay? All right. So what about something like this then? So let's think about this is weird. You've probably never seen something like this in math before, but a relation in math doesn't have to be between just numbers. I mean, it can be between things too, right? So here we got a menu in a donut shop, coffee shop, and we've got some items and the prices for each item. Okay, so what about part A? Is price a function of the item? First of all, how would I maybe write that function? So this would be price as a function of item, right? So let's let price be P and item be I. What would that look like? Yeah, okay, so, right, so we could say something like, if we wanted to, we could write this as P of I, right, equals some output, right? Another way we could, if we wanted to, we could write that as price equals some function of I, if we want to, where price is the output, whatever we're going to call the output of the function we're inputting I. This is the way we've kind of talked about it. Does that work? If I input an item, like what's an example of an item? Plain donut. If I input a plain donut into my function, what's it going to output? 149, a price, right? Does that make sense? So we've got price as a function of the item, meaning what I'm inputting. Okay? Does that work? Is that a function? It is, right? For every input, I get one output. If my input is a jelly donut, I get one price, right? So yes, the answer to this one is yes. Is the item a function of the price? It's not, right? Because in this case, that's the input, right? And item is the output. Everybody get that? When we say something is a function of something else, it's a function of the input. Okay, that doesn't work, does it? How come?
Because jelly donut and chocolate donut chips.
They're the same. If I go into that donut shop and I say, okay, I got $1.49, what do you got for me? And the guy says, well, only one thing. You can buy a plain donut. That works, right? But if he says I've got $1.99, then the guy, he's got to make a choice. There's two outputs. So that doesn't work. It's not a function if you flip it around like that, is it? So the answer to this one is no. Okay? How about something like that? So looks pretty normal, right? It's telling us if your percents fall in these ranges, say we're rounding to the nearest percent, these are the grade point averages associated with those. So is grade point average a function of the percent grade? So we're looking at this first, this is the question we're looking at right now, underlined in orange. Oops. I'm running out of virtual ink. So what do you think? What are we asking here would be the input for the orange one? Is grade point average a function of percent grade? So percent grade is the input, and grade point average is the output. Does that work? You're right. Good. It works, doesn't it? Right? Because if I input a percent grade, if I input 75, for example, there's only one output I get. It's 2.5. Right? Does that make sense? So the answer to that one is yes. Oops. What is going on with this guy? Okay, how about this one will be underlined in blue. So the blue question. Is the percent grade a function of grade point average?
No.
How come?
Because you could have like 265, 264, 225.
Ah, okay, good. Right? Does that make sense? So if I have a grade point average of 3, then that outputs to a whole bunch of different answers, right? A whole bunch of different outputs. So that one would be no. Okay? Like that. Oh, I guess it's supposed to be like all-time great baseball players, in somebody's opinion. Is the rank a function of the player name? So for part A, what's the input?
The name.
Name. Okay, good. So input equals name output equals rank.
Right.
Does that work?
Yeah.
Yeah, it works. Yes. Okay, how about down here? Oops. What's the input there? And the output, is that a function? Yeah, it is both ways, isn't it? Okay. So later on, we'll call that an invertible function, if we can trade around the domain and the range, right? And it still works. Okay, I think that's probably a pretty good place. I think that's probably a pretty good place for us to stop right there. How much, we don't have a lot of time, do we?
2 minutes.
10 minutes, yeah. Why don't you go ahead and just go to the first assignment. I bet you can finish it literally during class, but make sure you do at least like one question from each part, okay? And then we'll pick this stuff up, and then any leftover time you can just work on other stuff or ask questions.